Hello and welcome to the first episode of our video series on Choice of Reactor in Chemical Engineering. This series is based on key industrial concepts and academic principles from process design. Today's episode will serve as the foundation. We'll be exploring the core reasons why reactor selection is crucial, what decisions need to be made early in the design process, and how multiple reaction systems affect reactor behavior. In chemical engineering, process design begins with the reactor. Why? Because the reactor defines the transformation step, the conversion of raw materials into products. The performance of this reactor has a direct and significant impact on the economic feasibility, safety, and environmental sustainability of the entire process. A well-performing reactor maximizes conversion and selectivity, minimizes byproducts, and reduces the load on downstream separation systems. Conversely, poor reactor performance not only reduces product yield but also increases costs and can introduce serious environmental problems. Reactors don't just produce our desired product. They also generate unwanted byproducts. These may be toxic, unreacted intermediates, or simply waste. Managing these requires expensive treatment systems and adds to raw material losses. Therefore, an essential principle in green process design is, do not produce waste in the first place. Instead of relying on costly and complex waste treatment units, we aim to select and operate reactors in a way that inherently reduces or eliminates byproduct formation. Once the product specifications are set, the first design decision involves selecting the reaction path. Here's the thing, many chemical products can be manufactured via multiple reactions. These alternative pathways may use different raw materials, involve different intermediates, and lead to different byproducts. When choosing a reaction path, the following factors must be considered: the cost and availability of raw materials, the quantity and toxicity of byproducts, energy requirements, and importantly, the availability of catalysts. The reaction path with the lowest environmental impact and highest economic feasibility is usually preferred. However, at the early design stage, not all consequences of the chosen path are immediately visible. Yet, even now, it's possible to eliminate poor choices and shortlist viable ones. To illustrate this, let's take an example from your presentation: vinyl chloride, a key intermediate in producing PVC plastics. This compound can be manufactured via at least 3 distinct reaction pathways, each with different costs, raw materials, and environmental concerns. In such cases, the engineer must weigh all trade-offs: raw material sourcing, reaction yield, byproduct management, and catalyst efficiency, before finalizing the path. Once the reaction path is chosen, the next consideration is the type of reaction system. Reaction systems are not all the same. In fact, they can be classified into 6 broad types: single reactions, multiple reactions in parallel which can produce byproducts, multiple reactions in series where intermediates may convert into undesired products, mixed parallel and series reactions which combine both behaviors, polymerization reactions where molecular weight distribution matters, and biochemical reactions which require specialized reactor types and conditions. This classification helps determine what kind of reactor and operating conditions are suitable for a particular process. Next, let's dive into reactor performance, a central theme in reactor selection. There are several ways to evaluate how well a reactor is performing, and 2 of the most important are yield and selectivity. Let's define these clearly. Reactor yield refers to the amount of desired product obtained compared to the total reactant fed to the reactor. However, this can be misleading because it includes unreacted recycled material. Selectivity, on the other hand, compares how much of the desired product is formed relative to undesired byproducts. This is a more meaningful measure, especially when dealing with multiple reactions. Yield is helpful only when we cannot recycle the unconverted raw materials, such as in toxic or unstable systems. In most modern plants, recycling is common, so selectivity becomes the more important metric. For example, in a reactor system where multiple parallel reactions are possible, selectivity tells us how well the reactor favors the main product over side products. High selectivity reduces waste, improves product quality, and enhances economic return. It's also important to understand that conversion, how much reactant is transformed, is not fixed at this stage. While you need to make an initial assumption to proceed with design, actual reactor conversion will be adjusted later based on detailed modeling, cost analysis, and integration with the full plant. Why? Because conversion affects everything downstream: separation units, recycling loops, even energy balances. Still, we do make informed guesses. For example, for single irreversible reactions, an initial conversion of about 95% is typically used. For single reversible reactions, we assume conversion near 95% of the equilibrium conversion. These are starting points and will be revised during process optimization. Unwanted byproducts, unlike unreacted feed, cannot be recycled easily. They represent a double penalty: first, raw materials are wasted during their formation, and second, environmental disposal costs increase due to their presence. This means that your reactor design should aim for maximum selectivity at the desired conversion. Let's summarize everything up to this point. The choice of reactor begins with selecting the most suitable reaction path. We must consider raw material costs, catalyst availability, byproducts, and energy use. Reaction systems can be complex, and understanding their classification helps guide reactor design. Finally, we evaluate reactor performance primarily through selectivity and conversion, while keeping in mind that these are subject to change as the design matures. With these foundational principles in mind, we're now ready to go deeper into how different reactor types behave with these reaction systems, which we'll cover in the next episode. Thank you for watching this detailed introduction to reactor choice in chemical engineering. In our next video, we'll explore the behavior and selection criteria for reactors under different types of reaction systems, including single, parallel, and series reactions. If you found this helpful, don't forget to like, subscribe, and leave your thoughts in the comments below.